In this video, we're going to talk about conditional probability. So conditional probability is trying to find the probability that something happens given that something else has already happened. So in this case, this is the probability of B is happening given that A is already happening. And that's what conditional means, is that you've got some condition that's already been imposed on it. So notice the notation here. It's probability of B given that A happens. So we would write this as probability of B given A has occurred. So to write this, that formula is going to be the probability of A and B over the probability of B. So let's look at an example. We've got a contingency table here. And notice they've given us totals, so we don't have to add anything up. They've done all that work for us. So I'm just going to highlight those. That way they stand out a little bit more. So this table is showing the results of a survey used to determine the number of adults who receive financial aid from their parents for certain purchases, college tuition, car, and house. And we've got them split up by age. If one person is selected from the survey, what's the probability that the person received financial help from the purchase on a home, given that the person is between the ages of 29 and 39? So the probability that they're going to get financial help on a home, given between the ages of 29 and 39. So we need to find the probability that both happen, so that they're this age with that help. So 29 to 39. So we had 392 out of that 3190. 3109, excuse me. So the probability of A and B over the probability of A. So the probability that someone was in that age group would be 1,000 out of the 3109. So 1,000 out of 3109. And the way we divide fractions, we could think about that big division bar here as writing it that way. And then we would do keep, change it to multiplication, and then flip the second. And you can see how those are going to cancel. So 392 out of 1,000. And as a decimal, it's going to be 0.392. Now, that order, again, is going to be important because this would be different if we wanted to find the probability that they were age 29 to 39, given they needed help buying their home, or they received help buying their home. So remember our formula. Let me write that up here so we don't forget it. Probability of B given A is probability of A and B over the probability of that A. So the probability that both happens is still going to be that 392 out of 3109. But what's going to change is what's happening down here. Because now, instead of looking at those between age 29 and 39, I'm looking at those who had financial help on their home. And I had 1108 that received financial help on their home out of the 3109. So we would do keep Change that division to multiplication and then flip that second fraction. And you can see how those cancel. So we get 392 out of 1108 for that. So you can see how that's going to be a different decimal there. Let me divide that out so we can get a decimal approximation. That is about 0.354. So it's a big difference in those two numbers. So that order is important. So it's important to understand how to use that formula. And what's nice with the contingency table is that there's kind of a little shortcut that we could use. So let's think about what this is actually talking about. I'm going back to this first one, probability that they receive financial help on their home given that they were age 29 to 39. So what this is saying is out of those, how many need this? So out of the 29 to 39, so out of your 1,000, how many received help buying a house? Well, it's 392. So you can see how that ended up being 392 out of 1,000. So you could use a little shortcut there to help you get there, only if you have a contingency table. We could do the same thing with this one. This is the probability that we want to find the probability that they were between ages 29 to 39, given that they receive financial help on purchasing a house. So, given this has already happened, how many are in this age bracket? So, given that that has already happened, so we only care about that event happening, and then out of all of those, how many were in that age bracket? So it would be 392 out of 1108, which is exactly what happened when we did our keep change flip to simplify that fraction. Let's look at a product rule for probabilities. So when we want to find two events, and we're looking at the probabilities, now we're like, in this example, we are no longer drawing one card. We are drawing two cards. So we want the probability that the first one is this, and then the second one is this. So this and is different than and before. And before was one event having both characteristics. This is more like, and then this event's going to happen. So the probability rule is going to say the probability of A and then B happening is the probability of A times the probability of B given that A has already happened. So we got to think about what happened in that last event. And we could do this for more than two events. I mean, what if we were doing this for 3 events or 4 events? It would work the same way. So let's look at a few probabilities. So a box contains 4 red, 3 white, and 5 green balls. Suppose that 3 balls are randomly drawn from the box in succession, and we are doing this without replacement. What that means is once one ball has been drawn, it is not going back in to be drawn again. And we want to find some probabilities based on that. So, and we're going to use a more intuitive first to do this. So we want to find the probability that the first is a red, and then we get a white, and then we get a green. So how many balls do we have total? Well, we have 4 red, 3 white, and 5 green. And that's a total of 12. So we want the probability the first one is a red. There are 4 reds out of the 12. We are going to pretend that we selected a red ball the first time. So, and we're going to keep that red ball out. So now we are down to 11 balls. So you can see how that denominator changed. And we want the probability that that second ball is going to be white. And there are 3 whites remaining out of those 11. And then we're going to look at that third event. So we picked the red, and then we picked the white, and then we're going to pick a green. So now we've got 2 balls that's already been taken out. We have 10 left, and out of those 10, 5 are green. When I multiply together, I'm going to get 60 in the top and 1320 in the denominator. And that reduces the 1 out of 22, which is about 0.045. Okay, so that's doing that without replacement. Now, if I did this with replacement, what that means is that that first ball that I select, I'm going to throw it right back in the box, and it could be drawn again. So look how that's going to change here. So the first one's a red. There's 4 ways that could happen out of 12. So we're going to assume success. We're going to pull out a red, and it's like, oh, yay, we've got a red. Now we're going to throw it back in the box, and it could be drawn again. So now we still have 12 in the box if we do this with replacement. Out of those 12, 3 are white. So we assume we got a white one here. We're going to throw it back in the box again, and we still have 12 in the box. And then there's 5 that's green. So look how my probability is going to change here. My top didn't change in this case, but my bottom did. Now it's 1728. And when I divide, I'm going to get something that's a little bit smaller. So you can see how that probability is going to change depending on if I'm doing this without replacement versus with replacement. So let's look at part B. What's the probability that 2 white balls followed by a green ball are selected? And again, let's do this without replacement. So without replacement. So the probability that first ball is white, there's 3 out of the 12. Since I'm doing this without replacement, I assume I have picked a white ball. I now have 11 left. And if I pick one out, then that means I only have 2 white ones left that could possibly be selected. And then now I've assumed I've picked a white one on the first trial and the second trial. Now we need to look at that last trial. There's only 10 left, and I still have all the green ones in the box. So this is going to be 6 times 5, which is 30 out of 1320. It's about 0.023. So just for fun, let's do it with replacement so we can compare. So with replacement, the first ball being white has a probability of 3 out of 12. We assume we picked a white one. We're going to throw it back in. Now it's going to be possibly selected again. The probability that second one's white is also 3 out of 12. And then we want the probability of picking that last one that's green. We still have 12 balls in the box because we are throwing them back in since we're doing it with replacement. And 5 is still green. So we have 3 times 3 times 5 in the numerator. And then 12 times 12 times 12 in the denominator. So you can see how that answer is slightly different if we do it with replacement versus without replacement. And we're looking, when we solve problems like this, we are looking for those key words with replacement, without replacement, and so on. Let's talk about this idea of independent events. 2 events are independent if one doesn't affect the other one. So let's think about flipping a die and rolling, flipping a coin and rolling a die. If I flip a coin and I get a heads, that has no effect of what happens when I roll a die. So those are independent events. Now let's talk about a deck of cards. If I take a deck of cards and I pull a card out of the deck and then I put it back in, my probabilities are not going to be affected because I do it with replacement. If I look at probabilities without replacement, let's say I pulled out a card and it was the Ace of Spades, and I say I'm going to sample without replacement, what's the probability the second card is a spade? Now I have changed some probabilities because I'm doing it without replacement, so I no longer have 52 cards in the deck. If I have pulled one out, I only have 51 cards in the deck. So, how do we know if two events are going to be independent events? There's a mathematical way that we can look at it. So, if A and B are two events in the sample space, and the probability of B given A is equal to the probability of B, then we say they are independent events. And if the two events are independent, then the probability of A and B is going to be equal to the probability of A times the probability of B. Now, we're talking about events occurring in succession again, so this is really and then. Probability A happens and then the probability of B happens. Right? And dice is a great example to illustrate this because if I roll two dice, I am not changing they're independent events because the first roll doesn't affect what happens the second roll. It's always going to be completely random. So a pair of dice is tossed twice. What's the probability that the first is a sum of 7 and then the second roll is a sum of 11? So the probability of A and B is going to be equal to the probability of A times the probability of B. And these are independent events. So how many ways can I get a 7? So if you think back to that sample set for rolling two dice, we could have a 1 and a 6 and a 1, a 2 and a 5 and a 2, a 4 and a 3, and a 3 and a 4. So there's 6 ways that could happen out of 36. And then we want the probability that the sum's going to be an 11. So we could have a 5 and a 6 and a 5, 4 and 7, 7 and 4. So there's 4 ways that could happen out of 36. So the probability, the first roll is a 7, and then the second one is an 11, would be 6 over 36 times. Oh, hold on. Sorry about that. I don't know what I was thinking. I don't know why I went up to 7 there. We were looking at a regular die, 6-sided die. There's 2 ways I could get an 11. So it's going to be 6 out of 36 times 2 out of 36, which is 12 out of 1296. Which reduces a 1 out of 108, or about 0.009.